Okay, well, welcome to the first of 4 videos covering Chapter 11, Section 6. Each video is its own problem to work on, and we're going to develop them slowly. I'm not just going to give the problem and have you solve the whole thing all at once. So we'll do it in bits and pieces. They're all different types of problems. Certainly they're all under the umbrella of a first-order differential equation, but the equations are going to look different. But for the most part, you'll be able to solve these, and you'll get some guidance going forward. To prepare, what you need in order to participate in these videos you need 3 things. You need a pencil, you need a piece of paper, or pad of paper, as well as the ability to press the pause button. You'll also probably want to embiggen the screen so that you can see some of the math that will appear in the fine print. I apologize for looking grainy. In my spare time I look grainier than I do in class. So anyway, you're probably here to see the math anyway. So let's get started with our first problem, and I hope you enjoy doing it as much as I enjoy jury duty. Okay, our first problem is as follows. The rate that ice forms in a pond is inversely proportional to the thickness of the ice. Now what I would like you to do, dear viewer, is to come up with the initial value problem if y is the thickness of the ice, and we start with there being, the ice is just forming at this point. So you should pause now. And so the initial value problem, dy dt equals ky, where k is a constant of proportionality, which probably depends on things such as the shape of the lake and the temperature outside and all of that. And the initial condition that we're starting with here is that y of 0 is equal to 0. That's the initial value problem. Now, does this even make sense to have that dy dt equals ky here? Well, let's look at a picture of what's going on. So I know that looks like a photograph, but it's really more of a picture describing what's going on. Notice that as the depth increases, so as y increases, the ice that's being formed is further and further away from the cold source, right? We assume it's cold outside. The water underneath is not below freezing, or it wouldn't be the water underneath, right? And so as the ice layer moves further and further from the cold source, the rate of ice formation would be slower, and that's where the inversely proportional comes from. Now, we are given that it's inversely proportional to the depth it's a reasonable model, but you could say, well, how do I know it's not inversely proportional to the square of the depth or the square root of the depth? Well, that's just how this model works. Now what you should do is you should try to solve the differential equation as well as the initial value problem. So you should hit pause again while you do that. And here you see the solution. It's a pretty straightforward separation of variables problem. Because you've got the y in the denominator for the original differential equation, it separates rather nicely. And so here are the details. Notice that I didn't wait till the end to solve for c. In other words, I didn't solve for y and then figure out what c is. Algebraically, it's a little easier to do a step above, but it doesn't matter. You'll get the same answer. Okay? So here is what a graph of that's going to look like. So you're graphing the thickness of the ice. That's along the y-axis, and over time that's the t-axis. And like the physical situation described suggests, right, you have ice growth really quickly early on, but the further, again, you get away from the cold, the slower the ice growth is, which is why your square root curve kind of levels off there. Okay, and just like that, you've already made it through the first video with less than 5 minutes of recorded material. So tune in again next time when we'll look at another application from 11.6. Bye for now. See you soon.